In this lecture, we're going to talk about nonlinear regression. So we'll have two lectures on nonlinear regression. The first one's going to be sort of the introductory lecture, and then the second lecture will go into slightly more advanced topics. So let's just start off by reminding ourselves what linear regression is, and then we'll move on to what nonlinear regression is. So linear regression really refers to being linear in the betas. So it's any model where we can write our dependent variable y and we have some predictors x1 through xk, where we can write that a model y equals the sum of some betas times a function of the x's. Now that function of the x's can be arbitrarily complex. It's that it's a beta times the function of the x's, and that arbitrarily complex function doesn't have any betas in it. Plus, of course, we've got the random error attached. So that's the key point, is that the term linear refers to linearity in the betas, not necessarily the predictor variables. So we can put in squared terms, cubes, interaction terms, all that sort of fun stuff. Okay, so we could look at a model like this one, which is quite clearly nonlinear in its shape. But if you examine it, all of the weird stuff's happening in the x's. The betas are just it's a beta times some function of the x's. So beta naught is just a beta naught times 1, which is still a function of x's. It's not a very interesting function. It's a very simple one, but it's a function of x's that always maps to 1. For beta 1, the function is e to the x1 plus x2 over 10, and so on. So here we've got a linear model. So now let's talk about what a nonlinear model is. Well, interestingly enough, it's everything else. So if we have a model like y equals beta naught plus beta 1 e to the x1 plus x2 divided by beta 3, so we've got beta 3 in an exponent that's attached to beta 1, well, we've suddenly got a nonlinear model. We don't have beta 3 times a function of x's, it's actually built into that function. We have a lot of nonlinear models throughout science. Now, often it's the case that we can convert nonlinear problems into linear problems, and this is what was done for a long, long time, wherever possible, just because nonlinear regression is computationally more intensive. Of course, our computers have caught up to that, and so now we can just use nonlinear models where we want to use nonlinear models. So let's just briefly talk about transformation and what this means and what it doesn't mean. So we might have a nonlinear model like e to the y equals beta naught e to the beta 1 x1. So we've got beta 1 in the exponent, so this is a nonlinear model. And so, if we were to take the log of both sides, then we could say e to the y star, where y star is just the natural log of y, so we've done a transformation of y, equals the natural log of beta naught e to the beta 1 x. But the natural log of one thing times another is the sum of the logs. So that works out to be our transformed y equals beta naught star plus beta 1x. So if you just work through the math, it's pretty straightforward to get here. Noting that this new beta naught star is the natural log of the old beta naught. So it's not the same beta naught anymore. It's a new parameter, but it's still a parameter, and we now are left with a linear model. So it's not linear in y, it's linear in the natural log of y. And our parameters have a slightly different meaning, but we have taken an original model based on x and y that was nonlinear, and we've converted it to a linear model for x and natural log of y. Now, if we actually wanted to transform back to the original model to find out what beta naught was, we can just simply take beta naught hat as being e to the beta naught hat star. So we're just back transforming, noting that our original relationship beta naught star equals the natural log of beta naught can be inverted by exponentiating both sides. Now, in this particular example, beta 1 has the same meaning in both models, so there would be no need to do any kind of transformation for it. If you're looking at, say, confidence intervals and you were back transforming, you just back transform the limits of your confidence interval. Now, of course, we've seen this sort of thing when we're doing logistic regression and other sorts of models. Now, there's one thing to note that when we're doing this sort of transformation, we're not actually going to get exactly the same estimates. We have slightly different models. So the first thing to point out is that the expected value of a function of x is not equal exactly to a function of the expected value of x. They're pretty darn close, but they're not exactly equal. They're within a first order Taylor series approximation if you've ever run into Taylor series. But what that really means in this example above, that the expected value of y star, which is the expected value of the natural log of y, is not exactly the same thing as the natural log of the expected value of y. It's close, but not quite the same. And when we're doing our models, we're modeling the expected values. So we're estimating very slightly different things. So we're always going to get, in that second decimal place, some kind of difference in our parameter estimates. So we can't expect them to be identical. However, there's probably a bigger, more fundamental difference between these two models, which really revolves around the models, the error structure. So if we just go back to the slide before, I've just described the expected value of y and how the expected value can be turned into a linear model. But if we actually look at what we want in terms of y, we're either going to say y equals beta naught e to the beta 1 x plus an error, or so an additive error, or potentially we could have a multiplicative error where y is beta naught e to the beta 1 x times an error. So this multiplicative error would be centered on 1 with some random noise around that. Now, in the first model where we have additive error, if you take the natural log of both sides, we suddenly lose our linearity because the natural log of beta naught e to the beta 1 x plus an error is not the same as the natural log of beta naught e to the beta 1 x plus the natural log of error. Natural logs don't work that way, so log of a times b is log of a plus the log of b, not the log of a plus b. Now the multiplicative error works just fine. If you start with a multiplicative error structure on y, then you would have an additive error structure on the natural log of y, just because of how logs work. So the transformation that was undertaken in this example would make much more sense if you believed in a multiplicative error structure than if you believed in an additive error structure. So that's going to be another difference when you're performing these models. And this is the sort of thing where you really need to look at diagnostic plots to see if a transformation makes sense or doesn't make sense. Okay, now that's really all I want to say about transformation. We're now going to move on to nonlinear regression itself. So we'll start with an example. The Ricker curve is a interesting curve that's quite commonly used in fisheries research, and it models recruitment to some kind of density-dependent stock. For example, salmon recruits versus female spawners. Now, this model has a fundamental concept built in that as you have more spawners, if you're talking about salmon, at some point in time, you're not actually going to get more recruits. You'll actually get fewer recruits. And this is going to be because you might have a biological assumption that there's a fixed amount of food for the recruits to eat, and if there's too many recruits, a lot of them are going to starve, and basically the population's going to go over carrying capacity and it's going to crash. So the Ricker stock recruitment curve says there's going to be some optimal number of say, salmon that would return to produce the most number of recruits, or even differently, maybe an optimal number to return so that if you look at the yield of the difference between recruits and salmon who've returned because you couldn't catch them in a fishery, you could find an optimal value of how many recruits you'll get out. Now, one of the interesting things about the Ricker curve is that it can be quite sensitive to individual data points, and fisheries data does tend to be really noisy. And in fact, an over-reliance on this curve and other curves without incorporating uncertainty really led to the crash of the fisheries in the east coast of the US, particularly the cod fishery. However, the Ricker curve, when used appropriately, can be quite valuable. The model describing it is y equals beta naught times x e to the minus beta 1x. So in this case, if x would be the number of salmon spawning, y would be the number of recruits produced. So here's some data from fake trevally lactarius in the Gulf of Thailand. And the data comes from 1963 to 1972. This is kind of a classic data set. It's also one where the Ricker curve fits pretty well, so it's not always the case with fisheries data. So we're starting with this data where we've got salmon stock, spawning stock measured in thousands of tons versus recruits measured in millions. The way we're going to fit this model is we're going to use the NLS command in R. So NLS is our primary command for performing nonlinear regression. What it takes as inputs are a model description. We have to tell it what our nonlinear model is, just like we do in linear regression. But it also requires good starting values. And finding those good starting values is one of the primary challenges in nonlinear regression. Okay, so the general setup is going to be you'll type NLS and you're going to have some parentheses. You're going to describe your model in a fairly standard way, y tilde f of x. But then you're going to say start equals list and plug in the initial values. Your best guess for those, for whatever your parameters are. So if we're looking at the spawning data, I've got my recruits data. So the recruits ranged from 281 million at the peak down to 14 million at the low. And the spawning data, we had spawning biomass ranging from 1,980,000 tons down to 10,000 tons. Now here's a model that works quite nicely. NLS recruits, because that's our Y data, recruits tilde B0 times spawning, that's our X data, e to the minus B1 times spawning. So that's beta naught X e to the minus beta 1X. But I need to give some starting values for B0 and B1. So start equals list, B0 equals 0.3, B1 equals 0.0044. And I'll talk about where those numbers come from in a minute. But this is the general structure for the model. Okay, so the big challenge is often finding around numerical issues, which is really basically finding good initial values. So on the last slide, I said the primary challenge is finding good starting values. NLS uses an iterative fitting procedure. It's essentially a mountain climbing procedure. You're on a mountain, you want to get to the top, you figure, okay, well, I know which way is uphill, so I'll start walking uphill. And if I keep walking uphill, eventually I should get to the top. These procedures are pretty good as long as we can get them to the mountain. If we can't get them to the mountain, they're going to fall apart. Maybe we get to them to a side of a cliff and they fall off. So sometimes it's just useful when you're introduced to a new function to see what some of the error functions look like. So in this first failure, NLS failure 1, I haven't provided any initial values. I've just said NLS recruits tilde B0 times spawning times exp minus B1 times spawning, but I haven't said start equals list. And it says error in get initial, no get initial method found for function objects. Now that's because there are a few functions that have built-in methods for developing initial values, but this isn't one of them. So it just says it doesn't know what to do. The second failure, NLS failure 2, I have provided initial values, but they're just not very good ones. So in the second one, I've said my model exactly the same, recruits tilde b0, etc. But then I said start equals list b0 equals 0.3. Now that's actually a pretty decent initial value, but b1 equals 0.05 is not a very good initial value. And it tells me I've got an error in numeric, deriv, some other stuff, missing value or an infinity produced when evaluating the model. Basically, it's probably tried to take the square root of a negative number or the natural log of a negative number or divide by 0 or something along those lines, and the numerical procedure has blown up. And this is R telling us that it's had a problem. And we need to go back and start again. Not at all uncommon when performing nonlinear regression to have to work at those initial values, and you're going to see this error message from time to time. Okay, so how do we find good initial values? It really requires some kind of understanding of your underlying model. So if we go back to the curve for the Ricker model, what we see is it starts off with something that's pretty linear at the beginning, and then that linearity kind of dies off as the exponential term takes over. But if we want to find initial values, what we can do is around the smaller values of x where the linear term dominates, we can assume that e to the minus beta 1x is somewhere around 1. So basically, beta 1 is going to be small, so it'll be e to the minus a small number times another relatively small number, which should be close to e to the roughly 0, which is roughly 1. So what we're going to do is we're going to say early on in the Ricker curve, we can approximate it by y is about equal to beta naught x, and the other component, the e to the minus beta 1x, is really just the constant 1, roughly. So what I'll do is I'll take a couple of data points that occur early on, one close to 0, and then I had another data point. If I just eyeballing the curve, it looked like somewhere around y equals 200, kind of corresponded with an x of about 600. So from 0 to 600, I had a rise of about 0 to 200, so roughly a 0.3 rise. Okay, so that's a decent way to get the beta naught. So what can we do to find beta 1? Well, later on in the curve, the exponential term will really start to become important. So what I'll do is I will take that 0.3 that I'm using for beta naught, and then I'll take a large data point. So the data point 1980, 245. So that was kind of my most extreme value of x. And I just plug the 0.3 in, the 1980 in for x, and the 245 in for y, which leaves me beta 1 to solve for. So I have 245 equals 0.3 times 1980, e to the minus beta 1 times 1980. I do some math and I get an initial value for beta 1 of around 0.00044. Okay, so now I can stick those values into the NLS procedure and get my output. Now, I want to point out that I don't have to have perfect initial values. If you plug these values into the Ricker curve at the data points we have, you'll see that I've clearly underfit the curve. The curve should definitely be higher. I don't need to get close to the top of the mountain. I really just need to get onto the mountain for the mountain climbing procedure to work. Okay, so once we've found some decent initial values, we're going to say model 1 equals NLS, recruits tilde b0 times spawning, etc., with our initial values plugged in. R won't do anything. It just accepts that. It'll say, okay, fine, no outputs needed. You've assigned model 1 to be this NLS. Just like we might use the lm command. We could say model 1 equals lm y tilde x1 plus x2. So once we have a model of type NLS or of type LM or of type GLM, we can use the summary command. So I can say summary model 1. It spits out my formula right here. That's always good to check. Make sure you've typed in your formula correctly. It gives me my parameter estimate, so B0, the best guess, the standard error, a t-statistic testing the hypothesis that B0 equals 0, a p-value. Now, often in nonlinear models, there's no real reason why you would test versus 0, so this information here isn't necessarily that useful, but the estimate and the standard error are quite useful. I'll get our normal output, the residual standard error, so this is my best guess at how much noise is in the data. So 26.83 is our best guess for S, or for sigma. And it lets me know that I have 6 degrees of freedom. So I had 8 data points fit 2 parameters. There's also some convergence information here. It told me that it took 5 iterations, so basically 5 steps up the mountain to get to what it thought was close to the top. And this is a measure of how little it was changing. So essentially, it's pretty confident that it is near a top. Now, sometimes, depending on, you can imagine if you're looking at a mountain range, there might be lots of peaks, and really what you would want is to get to the highest of all possible peaks. The NLS procedure, if you're in a situation like that where there's a few possible peaks, if you start closer to a lower peak, you only get to the top of that lower peak, and it'll think it's converged. But most models, you really just have the one peak. So most of the time, it's relatively straightforward. But if you have a very complex model, it's good to try out a few different initial values to make sure you're getting to the same location. Okay, so from that curve, from that output, we get our estimated curve. So y hat equals 0.498x e to the minus 0.00685x. So let's just look at that. So B0, the estimate was 0.498. B1, the estimate was 0.00685. And our model is negative e to the negative B1 times spawning. So that's why there's the minus sign right here. Now, if we want to, we can calculate our approximate 95% confidence intervals for each of the parameters in the exact normal way. Beta 1 hat or beta 0 hat doesn't matter. So beta I hat plus or minus the correct t-statistic based on our residual degrees of freedom. In this case, that happened to be 6. If we want a 95% confidence interval, we look for the 0.975 t-statistic and multiply by the standard error of the beta I hat. So if we want to do that for, say, beta 0, we just say, okay, well, our best guess was 0.4983. The correct t-statistic is 2.447 based on 6 degrees of freedom. And the standard error from the model output, if we go back one slide, we can see that the standard error for B0 was 0.06385. So there's our 0.06385. Multiply that all through, and we get 0.34 to 0.65. That is, we're 95% confident that beta 0 lies between 0.34 and 0.65 with a best guess of about 0.5. Okay. We should also do diagnostics, just like we would do for any other model. We can plot the residuals versus the predicted values, residuals versus a covariate that's in the model, like in this case the number of spawners, or it could be against a potential covariate that's not in the model. Maybe we wanted a temporal trend or something to see if there's any pattern. And what we're hoping is that we don't see any obvious pattern. So in this particular plot, we're just looking at residuals versus predicted. There's no really obvious pattern here that would make us think we had any huge issues. In nonlinear regression, it is quite common that you might have unequal variance. So you might have smaller variance for smaller values, larger variance for larger values. And that sort of issue can be solved using a weights option. Basically, just like you can do weighted linear regression, you can do weighted nonlinear regression. You want your weights to be proportional to 1 over the variance. And But in this model, we're just considering we don't have any weights, and we look at our residual plot. We don't see any obvious issues, and so we say, okay, we're happy to go on from here. So the next thing we can do is add a fitted curve. So I want to draw a nice smooth curve because basically I want a pretty picture at the end of the day. So I'm going to have to come up with some new data points. So I say new spawn equals sequence 0 to 2000. That's because if I look at the spawning stock range, I went from about 0 to about 2000. So that's the range I want to draw from. And I picked a nice small number, 0.1. That'll just make sure that I have a nice smooth curve. That 0.1 is probably a little overkill in this case. I then use the predict command. So my estimated number of recruits uses the predict command. The model output, so my model was called model 1, so it takes all those parameter estimates for model 1. And I want to use the new spawn data for my spawning variable. So it'll just plug in these values of x, calculate a bunch of predicted values, and then I can draw a nice curve, nice line. So I've got my original plot, so my original data, I'm plotting spawning versus recruits. I've given it a nice label for both x and y. I've chosen a plot character. In this case, I've allowed default values for all sorts of spacing and tick marks and things like that. If I was to make a publication quality figure, I would actually care about every little detail. What's the text size, what's the spacing between the tick marks, and all that sort of thing. But this is certainly a decent enough looking figure for these purposes. And then I want to add my fitted line. I use the lines command to add a line to plot. I'm using my new spawn, so the 0 to the 2000 data, along with the predicted values for that. And there, that gives me my nice smooth line on top of it. Okay, so that's all we have to say in this first introductory lecture. In the next lecture, we'll go on and we'll talk about making confidence intervals and prediction intervals for a particular observation of x. So how accurately did we fit the curve at x equals 1000? And we'll talk about some extensions to the nonlinear model.